Hello and welcome. In our previous studies of trigonometry, we've focused heavily on right triangles, using tools like SOH, CAH, TOA. But what happens when a triangle doesn't have a right angle? These are called oblique triangles, and they require a different set of tools to solve. In this lesson, our main goal is to master one of those powerful tools. By the end of this video, you will be able to: first, define and apply the law of sines to find missing sides and angles in oblique triangles. Second, you'll learn to analyze what's known as the, quote, ambiguous case to determine if a given set of measurements can form 0, 1, or 2 triangles. And third, you'll be able to use a new formula derived from the law of sines to calculate the area of any triangle. Let's begin by defining our key tool for today. Let's define the law of sines. It's a fundamental relationship between the sides and angles of any triangle. Consider any triangle with vertices labeled A, B, and C. The angles at these vertices are also called A, B, and C. The side opposite angle A is side A, the side opposite angle B is side B, and the side opposite angle C is side C. The law of sines states that the ratio of the length of a side to the sine of its opposite angle is constant for all three sides of the triangle. Mathematically, this is expressed as side A over the sine of angle A equals side B over the sine of angle B, which also equals side C over the sine of angle C. This powerful law allows us to solve for unknown sides and angles in oblique triangles, as long as we know a side and its opposite angle, plus one other piece of information. So when can we apply the law of sines? It's most direct when we know two angles and one side. This falls into two categories: angle-side angle, or ASA, where the known side is between the two known angles, and side-angle angle, or SAA, where the known side is not between the known angles. Let's work through an example of the SAA case. In this triangle, we are given angle A is 70 degrees, angle B is 55 degrees, and the side opposite angle A, side A, is 12. Our goal is to find the missing angle C and the missing sides B and C. The first step is always the easiest. Find the third angle. Since the angles in a triangle sum to 180 degrees, we can find angle C by subtracting the other two from 180. So C equals 180 minus 125, which is 55 degrees. Now that we have all three angles, we can use the law of sines to find the missing sides. Let's find side B. We'll set up a proportion using the ratio we know completely, which is A over sine A, and set it equal to the ratio for side B. This gives us 12 over sine of 70 degrees equals B over sine of 55 degrees. To solve for B, we multiply both sides by sine of 55 degrees. Calculating this gives us a value of approximately 10.5. Next, we find side C. A good practice is to always use the original given values to avoid errors from previous rounding. So we'll again use the ratio of A to sine A. We set 12 over sine of 70 degrees equal to C over sine of 55 degrees. The calculation is identical to the one for side B, so side C is also approximately 10.5. Notice that angle B and angle C are both 55 degrees. In geometry, we know that if two angles in a triangle are equal, the sides opposite them are also equal. This confirms our result, that sides B and C are the same length. Now let's look at an angle-side angle, or ASA, case. Here the known side is between the two known angles. In this example, we're given angle A is 35 degrees, angle B is 25 degrees, and the side between them, side C, is 68. Just like before, our first step is to find the third angle, angle C. We sum angles A and B, which is 60 degrees, and subtract from 180. This gives us angle C equals 120 degrees. Now we have a complete pair, side C and its opposite angle C. We can use this to find the other sides. Let's find side A. We set up the proportion. A over sine of 35 degrees equals 68 over sine of 120 degrees. Solving for A, we multiply 68 by the sine of 35 degrees and divide by the sine of 120 degrees. This gives us approximately 45.0. Finally, let's find side B using the same known pair. The setup is B over sine of 25 degrees equals 68 over sine of 120 degrees. Solving for B, We find it is approximately 33.2. We have now solved the entire triangle. We've seen how the law of sinus works well for ASA and SAA cases. But there's a third situation that's more complex. This is the side-side angle, or SSA case, where we know two sides and an angle that is not between them. It's called the ambiguous case, because the given information might produce one triangle, two triangles, or no triangle at all. The outcome depends on the relationship between the given sides and the triangle's height, h. We can calculate this height using the formula h equals b times the sine of a, where a is our known angle and b is the side adjacent to it. Let's visualize the possibilities. Imagine we are given angle A, adjacent side B, and opposite side A. First, if side A is shorter than the height h, it can't reach the base. No triangle can be formed. Second, if side A is exactly equal to the height h, it forms exactly one triangle, which is a right triangle. Third, and this is the most interesting case, if side A is longer than the height, but shorter than side B, it can swing inward or outward to form two distinct triangles. Finally, if side A is longer than or equal to side B, it's too long to swing back, so it can only form one triangle. Let's apply this logic to an example where two triangles are possible. We are given side B is 100, side A is 60, and angle A is 28 degrees. This is an SSA case. First, we must calculate the height h to compare it with side A. The height h is b times sine A, which is 100 times the sine of 28 degrees. This gives us a height of approximately 46.9 meters. Now, we compare our values. We see that side A is greater than the height h, but less than side B. This is the exact condition for two possible triangles. So, we need to solve for two different triangles. Let's start by finding the possible values for angle B using the law of sines. Setting up our proportion, we get sine B equals 100 times sine 28 divided by 60. This gives a value of about 0.782. When we take the inverse sine, our calculator gives us one angle, which we'll call B, approximately 51 degrees. However, there is another angle in the second quadrant with the same sine value. We find the second angle, B, by subtracting B from 180 degrees, which gives us 129 degrees. Now we have two separate triangles to solve. Continuing with example 3, let's solve for each of the two possible triangles. First, let's consider the triangle with angle B equal to 51 degrees. We find angle C by subtracting A and B from 180, which gives us 101 degrees. Then, we find side C using the law of sines. C is approximately 125.5 meters. That's our first complete solution. Now, for the second triangle. This triangle uses the obtuse angle for B. B equals 129 degrees. We find angle C by subtracting A and B from 180, which results in a small angle of 23 degrees. Finally, we find side C using the law of sines. C is approximately 49.9 meters. So, we have found two completely valid triangles that satisfy the initial given measurements. This is the essence of the ambiguous case. Let's look at another SSA example, this time one that results in no triangle. We are given side B is 67, side A is 48, and angle A is 60.5 degrees. As always with the SSA case, our first step is to calculate the height, h. The height h is 67 times the sine of 60.5 degrees, which is approximately 58.3 inches. Now we compare side A to this height. We can clearly see that side A, at 48 inches, is shorter than the required height of 58.3 inches. What does this mean? Since side A is not long enough to reach the base from the end of side B, it is impossible to form a triangle with these measurements. Therefore, there is no solution. This check is crucial because it prevents us from wasting time trying to solve a triangle that cannot exist. Beyond solving for sides and angles, the law of sines also gives us a convenient way to find the area of any triangle. Let's derive this new area formula. We know the classic formula for a triangle's area. That formula is area equals 1/2 times base times height. Now, consider a triangle with base C, Let's draw the height h from vertex C down to the base. This creates a small right triangle on the left. In this right triangle, the sine of angle A is the opposite side, h, divided by the hypotenuse, b. If we rearrange this equation to solve for h, we get h equals b times the sine of A. Now we can substitute this expression for h back into our original area formula. Substituting, we get area equals 1/2 times c times the quantity b sine A. This simplifies to 1/2 b c sine A. This is a very useful formula. It tells us the area of a triangle is 1/2 the product of two sides and the sine of their included angle. This is a side-angle side or SAS configuration. We can write this formula in three ways, depending on which angle we know. All three give the same area. Let's practice using this new area formula with an example. We need to find the area of a triangle with side A of 200 feet, side B of 220 feet, and the included angle C of 40 degrees. We have two sides, and the angle between them, which is the perfect setup for our formula. We'll use the version of the formula that includes angle C, area equals 1/2 AB sine C. Now, we just need to substitute our known values into the equation. Plugging in the numbers, we get 1/2 times 200 times 220, all times the sine of 40 degrees. This simplifies to 22,000 times the sine of 40 degrees. Calculating this gives us approximately 14,141.3 square feet. Rounding to the nearest square unit, the area is 14,141 square feet. Remember to always include the correct units in your final answer, which for area will be square units. Finally, let's see how the law of sines can be applied to solve real-world problems. Here's a classic application problem. A fire is spotted by park rangers in two towers, A and B, which are 5 miles apart. From Tower A, the angle to the fire is 39 degrees. From Tower B, the angle to the fire is 58 degrees. The question is, how far is the fire from Tower B? The first step is to draw a diagram. The towers and the fire form a triangle. We know two angles, A and B, and the side between them, C, which is 5 miles. We need to find the length of side A, the distance from Tower B to the fire at C. To use the law of sines to find side A, we need its opposite angle, A, which we have. But we also need another complete side angle pair. We have side C, so we need to find its opposite angle, C. We can find angle C easily. It's 180 minus the sum of the other two angles, which gives us 83 degrees. Now we have the pairs C and C, so we can solve for A. We set up our law of sines proportion. A over sine of 39 degrees equals 5 over sine of 83 degrees. Solving for A, we get 5 times the sine of 39 degrees divided by the sine of 83 degrees. This calculates to approximately 3.17. So, we can conclude that the fire is approximately 3.17 miles from Tower B. Let's quickly recap what we've accomplished today. We've added a major tool to our trigonometry toolkit. We introduced the law of sines and saw how it allows us to solve any oblique triangle when we know two angles and a side, in both the ASA and SAA cases. We delved into the complexities of the ambiguous SSA case, learning that by comparing the given sides to the triangle's height, we can determine if there are 0, 1, or 2 possible solutions. We also derived and applied a new versatile formula for the area of the triangle, which is incredibly useful when you know two sides and the angle between them. Finally, we saw how these concepts come together to solve practical, real-world problems. Mastering the law of sines is a crucial step in your understanding of trigonometry. Thank you for watching.